Welcome to another episode of Code for Thought.
My guest in this episode is Derek Jones. I came across Derek on a posting in the RSE Slack channel. It was in reaction to his blog post he wrote in early 2021 called Research Software Code is Likely to Remain a Tangled Mess. The blog post caused quite a stir at the time, as Derek expressed some doubts that research software engineers will have a significant impact on what he says is often spaghetti code written by researchers. Kindly, Derek agreed to talk to me about his blog post. But first, let Derek introduce himself.
Oh, hello, Peter. Thanks for inviting me. So, my background is compilers and source code analysis. My company, Knowledge Software, has been going for, 36 years now. For the last 10 years, I've been working on a book, Evidence-Based Software Engineering, where I've collected all of the publicly available software engineering data. And it came out in November. It's a free download. So search on evidence-based software engineering, and I think I'm number one on Google.
I got intrigued by your blog post, Shape of Code and Coding Guidelines. And there's a post called Research Software is Likely to Remain a Tangled Mess. And I would like to take the opportunity to talk a little bit about that. So first of all, what made you write that blog post?
Well, the blog's been going for 12 years now, I think. And it started out as a way of me writing things down to get so that I could stop thinking about them all the time. I write something about once a week. And it's also useful for pointing people to some ideas I've had. I say, look, go and read about what I've said. I heard about sustainable software walking randomly, Mike Coucher. I heard about it a few years ago. And it struck me as a very naive approach. And
why is that?
Yeah, he was involved with sustainability. I think at the time he was at Manchester or Sheffield, or this was back when he was writing very technical posts, and I would follow his blog. He started writing about this. That's when I first saw it. Checked a few other posts, and I thought, well, these people just don't know what they're talking about. They know about how to write software, but they don't understand the processes involved, and they don't understand the ecosystem and the life cycle. They're sort of technical people who write software who jumped on this bandwagon. The whole thing was just so naive. I've got some background for quite a few years. I was involved with software portability. This was in the days before Windows and Linux or whatever took off, when software actually was very difficult to port, and you had to put a lot of effort into it. These days, it's really quite easy to port software. I knew a lot about porting software, and I realised that these people were running around like headless chickens. They didn't know what they were talking about.
So what exactly is it that you took issue with? I mean, what aspects do you think are naive?
You can make software certainly you can make it more portable and more sustainable. It's never 100%, but you can do a lot to make it more. But it takes a lot of time and effort and know-how. My experience is you have to port it to 3 different environments before you find out most of the problems. If you look at the people who are writing research software, they're mostly recent graduates. In industry, there's a steady stream of graduates coming in. So we know exactly how much graduates know. And it's not a lot, which is not surprising, really, because they don't spend a lot of time programming. And so you wouldn't expect them to know much. This sustainable software, or alleged sustainable software, is created by the people who are least qualified to do it, and who with the least amount of experience, and probably the least motivation. They want to get their papers published and their research done. And making it easier for other people later on to use their software it must be at the bottom of their list of things to do.
Which part are we actually talking about? Are we talking about sort of the research software engineering side, or are we talking more about the people who actually get thrown into the pond and say, okay, go swim and write software for a research project and then write a paper about it?
Everybody claims that what they do is best practices. That's true in academia and industry. So that's a buzzword that everybody uses, and it's completely meaningless. As far as I know, nobody's ever done a survey about what the best practices are. Nobody's ever run any experiments to find out whether best practices really are the best practices, or compare different people's best practices. The only way that you find out whether software is portable is by porting it, because it's about details, and that changes over the years. When I did it, I was always constantly surprised about you go to a new machine and something different bites you. You need a lowest common denominator, and it takes a lot of practice to find out what that is. On some systems, the clock is 50 hertz, and on others, it's 60 hertz. And that affects your timer resolution. And then you say, well, do I want to write my code such that I can handle both resolutions? Or am I happy just to go with one resolution? That's just one example. There's lots of trade-offs involved. A lot of software never gets ported to different platforms. So you say, well, why bother?
I would like to go back to the best practices a little bit, because you're right that sometimes best practices is used as a checkbox that people take off and use for marketing. But I think there's also a little bit more to it. I think we now homed into some of the best practices, which
have you ever
homes
seen
in on testable. Sorry?
Have you ever seen a study that compares best practices?
Well, I think there is actually something studies like, for instance, testing and testability of software. There is the practice of unit testing. There's the practice of integration testing. You may argue whether that is part of the best practice or not, but, I've seen a number of people identifying it as such.
Testing, I think, is something that would be practical and useful to teach people. I think sustainability, that's not going to happen. But a lot of software is not well tested. If the focus was on testing, you might actually get some benefit. But of course, you might not get funding. I'm sure the sustainability funding is coming from the fact sustainability is the in thing at the moment. You talk about sustainability, you can get funding. But I don't think it'll have any impact. But I think testing could have real impact, because you want to make sure that the software actually works correctly. That's the number one priority. And then once you're confident that it works correctly, then you start worrying about other stuff like portability and sustainability.
Maybe we need to home in a little bit about what we mean by sustainability, because there's this word hanging in the room.
Yes.
So what is your definition of sustainability? What do you mean by that?
I don't know what sustainability is. I know what software portability is, which is to minimize the cost of running it on different platforms. And you might have time portability, where if the software works today, is it going to work in 5 years' time? Because, of course, software depends on various third-party libraries, and those libraries evolve over time. I read a few days ago about a post about some climate software that was written in a language from the 1950s, and the people were complaining. And that struck me as, well, that is sustainable software. It was written in language in the 1950s, 70 years ago, and it's still with us. Well, that's sustainable, isn't it? It's the old stuff that is proven to be sustainable.
Okay, so I think sustainable then in the sense that it needs to have a lifespan that goes beyond a certain moment. So it needs to have durability. So that is certainly an aspect of sustainability. So would testing fall into the same category, where we could say, okay, in order to be a sustainable software, it also needs to be testable and tested. We need to be able to make some statement about the software as to how well or not it works.
You can have sustainable software that gives you the wrong answer and continues to give you the wrong answer forever. I mean, that's sustainable software, isn't it? It just gives you the wrong answer. So I think testing is something different. Testing is where does the software give you what is believed to be the correct answer? Having tests is a part of sustainability, in the sense that if 5 years from now, if I'm running your software, I say, well, does it work? If I've got a bunch of tests and I know what the behavior of these tests should be, I can run the tests and confirm that, yes, the software still gives the answers it gave 5 years ago.
I think sort of when we talk about sustainability, then we have two aspects, one of which is sort of the testing aspect, and the other one is the durability. We want to make sure that the software 2-3 years down the line, when maybe another researcher picks it up to do his or her analysis and wants to use that, they could. In the end, we did actually end up with two quite powerful definitions of sustainability.
Well, testing is a way of checking sustaability.
Yeah, but it's related to it. So you can't sort of think about sustainability without actually having the testing aspect in it, surely.
Today, if I take your software and you say it works, but there are no tests, how do I and I build it on the same system as you did today, how do I know it works without tests?
Indeed, exactly. In order for software to work, we need to be able to make sure that the software actually does work.
We need verification.
We need verification, exactly. So verification is effectively an expression of how sustainable the software is, because if you can't verify that, there is no chance in hell that you can actually keep it sustainable, keep it going. If it's not working today, then it's very unlikely it's going to work in 5 years' time.
Well, yeah, it's not magically going to start working, but it may magically stop working, but it's not going to start working.
Exactly, yes. You made it stop working, but not start working. Going back to research software then, because the article goes specifically about research software that is likely to remain a tangled mess.
Yes.
What do you think we would need to do in order to get out of it? And do we actually need to get out of it? Is it actually okay to have it as a tangled mess, in your view?
All programmers start by writing a tangled mess of code because they don't know any alternative. How do you get out of the tangled mess? And there was a later blog post where I spoke about that. Mm-hmm. You show people, well, what are the benefits of doing it an alternative way? The benefits are that you can write bigger programs. The problem with code is you have to fit it all in your head to understand it if it's a tangled mess. And if you introduce some bureaucracy, you can reduce the amount of code you need to keep in your head, and therefore you can deal with bigger programs that they're just easier to maintain because you don't have to think about so much. So how do you get people out of the tangled mess habit? It's training and it's social pressure. If you're in a group of people and you have a beginner come in, you can say, well, look, this is how we all do it, and they have to do it the same way, and they can see everybody's doing it that way. But if you've got a researcher working on their own, there's no social pressure on them to change their ways. And you might say, well, is it worth a worthwhile investment on their time to learn to do it differently? And I don't know the answer to that. If they're not writing much code and they don't care what happens to the code in the future, then it might be more cost effective for them to carry on doing what they're doing, just carry on writing a tangled mess. It doesn't matter. Or rather, it's not cost effective from their point of view. Whether it matters or not in the future, we don't know.
You know, from a researcher, if I'm doing, say, a degree in biology or medicine or physics or whatever it is, then I have a certain research project and a subject, and I would like to get on with it. At the end of it, there is a paper. The software is basically a way to meet that requirement if I need to write my own software. So in that case, I probably don't expect that to live on. I guess what I'm getting to is, do you see there is actually a role that we can define, sort of apart from the researcher focuses on the research, and we actually have, in addition to that, people who focus on the software.
Software is a craft in the sense that you learn it by doing. How do you put the pressure on the researcher to invest in learning to write software in a different way? So you're asking them to make a time investment in learning to do things differently.
We are asking them to, they could make the time invest them themselves, or they could actually use part of the funding to actually go to people who know what they're doing. That is sort of the research software engineering groups that we have established in universities now.
If the software is written by the researcher, they have to change their way of doing things, unless they've got a team software engineer who's just going to rewrite it all for them. You've got to teach them, look, this is how it's done, and they have to invest some time to start doing it that way. They need to be with someone who knows how to do it and ask them, and basically be in the same room. I'm used to dealing with people who write software continuously. If you get someone new in, after about 6 months, they basically get the hang of the direction they should be going in. If you're dealing with someone who just writes software occasionally, then it's going to take a lot longer than 6 months.
I think what we also need to recognize is that writing software in research may not be a one-off, though. Some of the software in research projects is being used actually for quite a long time. So it was designed and written originally for, say, a short-term project, but then somebody realized, oh, hang on, if I change the parameters like that, then maybe I can use it in a different epidemiological model, just as an example. So these things then have a way of hanging around. So the investment is actually training people up. Wouldn't you say that from that perspective, it's not a bad thing? You know, you want to do good research, you want to keep in research, you need to learn how to write software, at least to some extent.
In industry, it was thought for a long time that software lived for many, many years. And in fact, the original paper, there was a book called The Leprechauns of Software Engineering. The author traced back to the original paper and found it wasn't based on any data whatsoever. And it was just folklore. It's not true. And I managed to track down some data that showed that software has a relatively short lifetime. And in fact, it's more cost effective to write software without worrying about future maintenance, and then to invest the money, to wait to see what survives, and then spend the money later on the software that actually turns out to have survived.
That's some kind of software Darwinism then, is it?
Yes. I'm getting a lot of pushback because, of course, people invested a lot of their resources and their time and their status on the idea that software has to live a long time. And so they don't like the idea that actually you just work, you pay for what survives and everything else dies young. And now, is that true in research software? I suspect it might be true, but we don't know. Now, if research software also dies young, the same conditions apply that, okay, it dies young, therefore it's more cost effective to spend money once the software has survived a certain amount of time.
Well, I think sort of it's probably the same as with the industry. So because in industry, you're right, there are some software that doesn't live for very long for various different reasons.
Well, most
right?
software
So it
doesn't
might
live
be.
very long. I have the data.
Yeah, you do also get, for instance, I worked in physics, and there are, in high energy physics, if you think about experiments like CERN that run really for a long time. So software really needs to be sustainable and has a long lifespan and measured probably not only in years, but probably in decades. I think it's kind of a mix, really. So in industry, you also have software that actually needs to work for a longer time before it gets overhauled.
But
And
the trouble is, you never know what it is in advance.
no, you don't. No.
I've seen some of the CERN software, and you think, well, is this the original, or has bits of it evolved over time and been replaced? So the main packages, I'm sure, are there, but have the components of the package chopped and changed over time. So I think it's well, certainly in industry, it's very difficult to predict what's going to be here in 3, 5, 10 years' time. And I'm sure the same is true in academia.
Which brings us back, because you don't know what the software actually ends up doing in, say, 3 or 5 years' time, or even beyond that, isn't then the right approach to say, okay, we take things like we define best practices to be that it needs to be tested, it needs to be testable, and it needs to have a way to verify the output. And that is sort of a first step to actually say, okay, that has a chance of actually surviving. We don't know if it will, but actually it has the chance of doing that.
Testing should be a separate thing. You should say, well, I want to be confident that the software behaves as I expect. Therefore, there must be some tests. If you haven't tested the software, you've got no way of knowing whether it works. That is a component of future sustainability, but it's also a standalone thing for here and now. If you give me some software, I say, well, Peter, how do you know this software gives the answer? And you say, well, it looks all right to me.
Well, yeah, I hope that I would say something else.
If you turn around and say, well, here's a whole load of tests I've
yeah.
then I go, oh, okay, right, that's new. You know, you've gone up in my estimation. You've written some tests. Most people don't, including me, I ought to add. That, I think, is where the effort ought to go. If you've got money to train people, it should be to train people to write tests. Testing is a skill. A lot of people, you say to them, well, write some tests, and they give you a blank look. And they say, well, the equations are okay. We know, it's mathematics, that works. And you say, yes, but the software implementation of the mathematics might not. There are all sorts of different ways that software can break. And certainly with beginners, they're always amazed that they say, well, I looked at this code and I didn't see the problem. And you say, well, look, it's not working. It takes a while for people to get over this, accept the fact that they make mistakes.
There is quite a gap between what is a test, how do you test it, how do you go about it, and then the other side of the coin, which says, okay, there's test-driven development, and you do that right from the beginning before you write any line of code. You actually think about how you would test it. That gulf is actually still needs bridging, is what we're saying.
Well, the test-driven development, that's a very disciplined way of writing. I know people who've tried that and then stopped it, and that's a fad in some circles, and I know some companies who do it that way, and I've never seen any experiments to show that that's the most cost-effective way of doing things. People say, well, test-driven development is code has fewer bugs. Well, that's true because you're writing tests and most people don't write tests. Anything that makes people write tests is going to reduce the number of bugs. I don't see that working in a research environment. It just requires too much discipline. And beginners just don't understand testing. They think that they've written some code and it works. They haven't yet experienced the degree to which they make mistakes. Learning to program and becoming a successful programmer is just accepting your own fallibility.
Also approaching problems in a structured manner. I think that's also part of the thing. And I think that's part of the training, or should be part of the training, that we teach people that you don't just go about and write code in a random fashion. You have to make sure that it's actually verifiable and testable. And I think it takes some discipline. That's right. It takes some training for sure.
It's not about teaching. It's about training. You have to sit people down and spend a few weeks with them and get them to go through the process.
I agree with that. I think we're coming a little bit towards the end now, but there is one thing that maybe we can help listeners with? Because people talk about spaghetti code, and I quite like that phrase, and I think you're familiar with it, I'm familiar with it. But how do we recognize spaghetti code? What is spaghetti code in your view?
It's where you have to understand all the code before you can make any changes. Everything connects to everything else. It's like a stream of consciousness. People have just written down things as they come to mind. So let's say you've got 1,000 lines of code. To modify that 1,000 lines of code, and it's spaghetti code, you have to understand all 1,000 lines.
Is it a little bit like James Joyce, Ulysses versus a structured poem?
The idea, well, what is not spaghetti code? Perhaps talk about that. Again, if you've got, say, 1,000 lines and it's more structured, it might be structured into, say 5 groups of 200 lines. That's just picking numbers out of the air. So to modify the code, you would only need to understand 200 lines rather than 1,000 lines.
One aspect then would be to be able to look at parts of the code in isolation and be able to understand it. With structured code, that would reduce the spaghettiness, if you like.
Well, it reduces the need to know. With spaghetti code, you need to know the entire program. With structured code, you only need to know a much smaller part of the code. Mm-hmm. And if you make a change to the much smaller part of the code, it will probably only affect the much smaller part of the code. With spaghetti code, if you change line 100, it could affect any of the other lines.
I would like to finish with the book that you wrote, Evidence-Based Software. What do you hope that readers will take away from that?
As a commercial compiler person, I was always interested in optimization. And someone would say you go to a customer and say, well, buy my compiler, it will make your code faster. And they say, well, how much faster? and so what you want to do the optimizations that give the biggest impact. And what are those optimizations? Well, the only way to find that out is to measure code. So I was always measuring code to find out how I could optimize the code. And then when I got into static analysis, finding bugs in code, you look for the common cases. Because you go to a customer site and they say, well, where are the bugs in my code? Again, you look for the common cases. What are the top 10, 100, 1,000 cases of things to look for in their code? Again, so it's studying code. And I knew there wasn't much evidence in software engineering. So I thought, well, it would be interesting to gather all the evidence up and write a book on it. There turned out to be about 2 or 3 times more evidence than I thought there was. So I've collected about 600 odd data sets. And if you think about it, it's amazing that one guy can go and collect all the available evidence on software engineering. So that's how much there is. It's such a tiny amount. It's unbelievable. Well, it started a discussion because now I can say, when people say, well, yeah, there's evidence, I can say, no, there isn't. I've collected it, and this is what evidence there is. So I think the main impact of the book is to show how little evidence there is.
Evidence in terms of how well software performs and how...
Well, things like maintainability, readability, all this nonsense about best practices, all the claims that people make. There's no evidence for any of it. It's all marketing hype. So one of the few findings was software lifetime, that it's actually a remarkably short lifetime. That's one of my few finds, discoveries I've made. I found enough evidence to be able to show that software has a short lifetime. And I'm getting a lot of pushback from people saying, no, it's not true.
You obviously only have access to public available data.
But
the software is written, it's not publicly available.
There are no secret repositories. I go to companies and say, can I have a look at your data? I offer to do a free data analysis. Let me make the data available in an anonymized form. And most companies don't keep data. The only time I've managed to acquire data is when it's been accidentally kept. So there are no secret repositories. Don't go down that path.
I don't mean secret repositories, but I'm just thinking about, there are private repositories on GitHub.
That's like pointing at the jungle and saying, well, look, there's lots of data in the jungle. Look at all those animals. But you have to go and collect the data. Because people point me at GitHub and say, look, there's loads of code. Yes, but you have to go and measure it. And it's not human code. It's just human data. For instance, if you want things like software estimates, that data's not on GitHub.
Okay, but certainly a discussion that gives us food for thought. And what are your plans with the book then?
Well, the book's out, so I had 250,000 downloads, which was good. I don't know how many people actually read it rather than just looking at the cover. So
I guess the fact that they download it is probably an indication that they're interested.
Well, I'm getting about 10,000 a month at the moment, so we'll see how long that keeps up. Because I'm still collecting data, so I sort of I've started calling myself a gentleman researcher. So I'm trying to collect data on various things to try and actually come up with some real know-how about how software works. And it's good I can point people at the book. So I'm hoping that a small group of us will actually make some real discoveries. We have some data and we'll see what happens. People have certainly started reading the book and coming up with ideas for things to do.
I quite like the title, right? So, and I do agree that you mentioned a number of points, like, for instance, estimation processes, and it always looked a little bit like black magic sometimes. There's certainly a lot of hype out there with regards to some of the practices. I wouldn't quite agree with all of them being just marketing. I think there are some practices that actually are reasonably well established, but I think it's certainly worthwhile thinking about and writing about and having some data about.
So how can I convince you that they're all hype? You're unwilling to give up on that?
I am unwilling to give up on that.
Well, if I turn around to you and say, well, where's your data? What are you going to do?
Well, I think it's not so much that there is no data, because there is. It's just not that there is an aggregate data. I can't sort of point you to say, okay, this is what best practices look like across different companies.
Where is this data?
I mean, what kind of data are we talking about, first of all? Right. I mean, we're talking about, for instance, I'm talking about testability, right?
Okay.
So we're talking about testability. We're talking about the metrics such as code coverage.
Code coverage is a great metric. I'm a great fan of code coverage, yes.
We have a code coverage. There are tools available that measure it. And that goes into the project details or the project data.
Do you know how many projects
for that project?
Do you know how many projects actually measure and record code coverage?
We do, and we did.
Wow. Okay, good.
Yeah, we did. And that's why I mean that it's not just marketing hype. So we did take that actually quite seriously. There is static analysis tools that we also used. And our team wasn't sort of the super duper developer team. I've seen other teams doing that as well. So
it's quite.
The data may not go into an archive and that then can be queried and do aggregate data and get some statistics on, but it has actually been used in teams, and I'm sure there are other teams out there.
There are teams, but it's quite rare. I'm impressed that you were doing this. There are very few people who do coverage, and unfortunately, there are even fewer who keep the data. Unfortunately, people just don't keep the data. They throw it away, which is very irritating.
Exactly. So because that's why I mean that, we need to be careful what we're saying, that the aggregation of these data may not be possible because they think, oh, the project is now done. I no longer need it. Why would they want to keep the data? So we finish a project, the product is out there. What do you do with the data? Why would you want to keep, your code coverage from week X?
Yeah, exactly.
It has no relevance anymore. But I mean, it has relevance, for instance, for people like you who want to look into that and say, well, how many people are actually doing it and what is the evidence for them doing it?
There ought to be a correlation between coverage and number of faults discovered in the field. And you say, well, the higher the code coverage, the fewer the faults. And I've yet to find a data set that would enable me to show that.
Okay, Derek, that was a fascinating conversation. Lots to think about.
Well, thanks for the chat, Peter.